Yeah, thank you very much. Oops. Yeah, so actually, let's just go right to the outline here. This is going to be a kind of microscopy talk because one of the sort of passions that I have and my lab has is trying to take new approaches to understand materials and solve problems in magnetism. So I'm going to try to tell you about three different things. If I run out of time, Giovanni, just get your big hook and, stop me. So the first one I'm going to talk about is a rather unusual kind of magnetic microscopy that is both time resolved and spatially resolved, in which we use spin thermal interactions to image magnetism. We'll talk about trying to make that a very high resolution technique. And I'll also tell you about some of the work that we've done on some antiferromagnetic materials that have interesting properties and remaining puzzles. And then at the last part, we'll switch to a different technique because, again, the puzzles are remaining, in which we'll scan a single NV center as a single spin probe to measure magnetic fields very close to the sample and use it to understand the antiferromagnetic insulator alpha hematite. Okay, so let's start with this idea of magneto-thermal microscopy. This is a spatiotemporal magnetic microscopy that is a little bit strange when you think about it because it's using very esoteric physics. The principle of operation is that we try to heat up our sample in a very local way. And throughout this talk, the most common way that we'll heat it up is either using, just focusing light very tightly onto a small part of the sample, or even to get even smaller, using a sharp scanning probe tip that has light focused on the end of it. And then that sets up a very local temperature gradient inside the sample, and that temperature gradient can couple to the magnetism of the sample in one of two ways. So if the material is a conducting magnetic sample, then there's going to be an anomalous Nernst effect. This is just the thermal dual to the anomalous Hall effect, and in such that you get a electric field when you have a cross product between M and the gradient. So the typical geometry for our experiments are that we would look at an in-plane magnetic moment in which there's an out-of-plane temperature gradient generated by our heat pulse, and then the electric field would be collected by the electrodes of the sample if the magnetization is along the y-axis in these coordinates over here. Let me get my laser pointer. Okay. And then the other thing that you can do, and I'll show you this as well, is you can study samples that are magnetic insulators. But in order to study that, you want to make an interface with a heavy metal with strong spin orbit coupling like platinum, and then the combination of the longitudinal spin Seebeck effect, which is pushing a spin current along the direction of the temperature gradient that pushes it into the platinum, and then it gets transduced into an electric field by the inverse spin Hall effect. So just to clarify what we're doing, in all cases, we're putting in a heat pulse and we're measuring a voltage. So the voltage is shown here. These are the two important terms. In all of these measurements, we're basically going to be measuring the MY component of the magnetization. And I also want to point out this second term, which is kind of boring if you think about it, but it turns out to be really exciting in terms of what you can do with it. So if you heat up a sample and the sample has conductivity, so whether it's your sample or if it's just the platinum on top of your sample, that sample's resistivity will generally depend on temperature. And so if there happens to be a current flowing through the sample, then you get an extra contribution to the voltage, which means that you can measure current density within the sample, which is very interesting when you're thinking about manipulating magnetization using currents. Now, just to put in perspective the properties of this as a microscopy, so the spatial resolution of the technique is purely based on the area of the thermal excitation. Lots of work has gone into that conclusion that I won't go into detail with now. But what that means is there's no intrinsic diffraction limit here. So we can use focused light to get focused light spatial resolution, but we can use other techniques to do even better. And at the same time, we can get good temporal resolution. Now, normally one would think of thermal diffusion as a slow process, but when you have a very thin film of material, only a few nanometers to tens of nanometers thick, then the time scale for the relaxation of the temperature gradient within the thickness of that sample is actually very short. It's on the scale of 10 or so picoseconds, and that means that you can stroboscopically use this effect as a probe to study the dynamics of your sample. So here's the take-home message for this part of the talk, and if you remember nothing else, this is what I would say. Is this sort of magneto-thermal microscopy, which again sounds a bit esoteric, is actually quite useful. So you can use it to study a wide variety of magnetic materials. So here I'm showing you images that we've done of ordinary magnetic metals like cobalt, iron, boron. This is actually a map of the dynamics of yttrium, iron, garnet, a magnetic insulator studied through the spin-Seebeck effect. This is the amplitude of FMR right here. You can look at antiferromagnetic materials. So here is the uncompensated spins in iron rhodium in the antiferromagnetic phase. And here is the spin-Seebeck effect of nickel oxide showing the current nucleation of domains. Surprisingly, it's a relatively high sensitivity technique, regardless of its kind of esoteric origins. So we're routinely able to get sort of a few tenths of a degree per square root hertz sensitivity to angle in the plane of the sample. And again, there's good spatial and temporal resolution. Now, the other take-home message is that it's just not limited by the diffraction limit, because it's not actually a light technique, it's a heat technique. So what I actually want to start by telling you about is how we've been pushing this technique to become a simultaneous way of measuring magnetization on the sub 100 nanometer scale, but also a probe of sub 100 picosecond dynamics. So let's start there. The basic idea here is that when you have a sharp tip and the tip is metal, then you can get very sharp electric field enhancement in the vicinity of that sharp tip. Now, the motivation for this work is to try to combine the spatial resolution that you can get from this sharp tip with the temporal resolution that you can get from a pulse laser. Just to put that in context, there's many techniques of microscopy that can give you one or the other. So for instance, this is work from my colleague David Muller here at Cornell, and he's showing magnetic skyrmions imaged with Lorentz tachography using a transmission electron microscope. And the spatial resolution is 1 nanometer. It's fabulous. On the other hand, this is a static image. It can't move. We can't see anything happening dynamically. In contrast, you can use a femtosecond laser and you can get the best results using magneto-optical techniques. And I'm sure Margaret will tell you some really great innovations from time-resolved X-ray techniques from her lab. But the bottom line for us is that there's very few opportunities to combine both nanoscale spatial resolution and picosecond temporal resolution. So that's really our goal. All right, so this is work done by my postdoc Qi Zhang, who just recently left for greener pastures in the land of sun. But what she did here is she focused light onto the scanning probe tip. This is a gold metallized tip, and brought it down in contact with a magnetic sample while she's shining light onto the end of the tip. And when the sample, which is in tapping mode, so it's going up and down like this, is starting to approach the sample, you basically don't see much of a signal. And then as it suddenly comes into contact, which you can notice by changes in the probe frequency and amplitude, that means it starts to interact with the sample. We also see an uptick in the magnetic signal as well as the current signal when we apply a current to the sample. So this really verifies that we have a near field interaction, and now we can go on to investigate what kinds of resolution we get. So to do that, we took a very boring, simple sample, which is just a cobalt iron boron sample. It's 5 micron wide bar with contacts at the end. We shine a laser again onto the probe, but this time we're taking line cuts, scanning across the sample, and we're looking for this magnetic response through the anomalous Nernst effect. And so what we see is that we indeed see it when we jump onto the sample. The signal goes up from, you know, sort of nanovolt signals to a few microvolt signal, and then back down again. And when we reverse the direction of the magnet along the y direction, then the signal also reverses. So this is very promising because it tells us that the sample is behaving the way that we expect it to, the signal is. We can also repeat the experiment in the current imaging mode, in which we apply a current density through the sample. And again, we see that it nicely images the dimensions of the sample in high resolution, and it respects the direction of the current. So this is all very promising. So then we can go ahead and take some images. So this is the same sample. It's 5 microns wide. It's just a soft cobalt iron boron material. And we can simultaneously image domains in this material using focused light far field imaging. And then also we can separately demodulate the signal with respect to the probe oscillation, which gives us the near field signal. And what we can see is that the near field image is much, much higher resolution than the far field image. As we dove into the analysis of this work, we realized that actually when you have a soft material, you don't have very sharp domain walls. So this image doesn't help us to actually learn what is the ultimate spatial resolution. And so we would have to try to contrive some way of getting a very, very sharp domain wall. And that actually proved to be a challenge to do it very controllably. So what we decided to do was use the current imaging mode as a way of probing the spatial resolution of our technique. And the idea here is that current is very easy to control just by lithography. So you can take some sample and you can just go into the clean room. We have a great clean room at Cornell. So we use e-beam lithography and pattern a very small constriction for the current like this. And then we can pass a current through it and use our current density imaging mode of the microscope. And what we find is that indeed we get a very sharp response right associated with that position in the topography where we have a sharp feature. Now, if we make a detailed comparison, and here's again a larger view of that sample, there's actually 2 constrictions, one at the top and one at the bottom, and we take a line cut through both of them. We can make a detailed comparison between the focused light version of our microscope and the near field scanning probe version of the microscope, and you see a very big difference. So this is kind of high numerical aperture focusing, and you get spatial resolution, you know, almost, but not, you're just a little bit below 1 micrometer. It's something like 0.7 micrometers. And then if you compare that to a separate measurement where we do it the same thing again using the near field probe, you see these much sharper responses. And the nice thing about current again is that it's really very predictable. So we can go to our finite element solver and we can calculate exactly what is the current distribution. And once we know that, we can deconvolve the data and understand carefully what is the instrument response. And what we find is that when we model the instrument response with a Gaussian, the Gaussian width is 74 nanometers. Or if you like, the full width half max of that Gaussian is 165 nanometers. So this is less than a quarter of the resolution of focus light. So we've quite far exceeded the diffraction limit here. And just, you know, after imaging the tip in the SEM, we find that the tip radius was about 65 nanometers, which is quite consistent with what you expect in a near field experiment. The resolution really is just a function of how small is the tip radius. Okay, now I promised you that, you know, we were motivated by keeping the temporal resolution. So we wanted to show that that was also present. And so we looked at that for both magnetic signals and for current density signals. And the simplest way to sort of guarantee that we have a stroboscopically time-resolved response is to directly resolve the duration over which the stroboscopic signal collapses. So this is saying we come in with our pulse from the laser on the tip, and that heats up the sample for a very short amount of time. And then we can try to measure that by essentially electrically mixing the signal that is coming from the sample with a reference voltage that we have in a signal generator. The signal generator can produce pulses that are about 100 picoseconds wide, and then we can scan their relative delay, and we combine these two signals on a mixer and amplify the result. And we find that what we're really measuring here is the convolution of these two pulses. And when we do this for the magnetic signal, which works for both signs of magnetic orientation, that we get something that's like 100 picoseconds. When we do it for current density, we also get something that's like 100 picoseconds. And because we know that we're measuring the convolution, we know the response must be actually below that. So probably, COMSOL modeling suggests that the anomalous Nernst effect in these samples is actually about 10 to 20 picoseconds. Okay. All right. And so, for the current imaging, one of the neat things that we were able to show here is that you can actually make a phase sensitive measurement of microwave current density using the scanning probe tip. And so we do a similar measurement to the one that I just described, except we're applying microwave current at 3.5 gigahertz to the sample. And then as we vary the delay of the microwave current with respect to the stroboscopic probe, we can see now this sinusoidal oscillation, letting us know that we in fact have a stroboscopic probe that is phase sensitive to this current. So this is pretty neat for understanding, how magnetism responds to currents. Okay, so now what I want to do, and I want to maintain the time here, is tell you about how we're using this magneto-thermal microscopy to look at some interesting materials. So I want to quickly introduce you to the material, one of the materials we've looked at, which is iron rhodium. Iron rhodium is kind of like the platypus of antiferromagnets. It is got a metamagnetic phase transition at around 400 Kelvin at 50-50 stoichiometry. So if you measure the magnetic moment as a function of temperature, it looks like this. You actually see hysteresis in temperature. So it goes through a phase transition, and then it goes from an antiferromagnet to a ferromagnet, and then you come back, and if you kind of overshoot the original phase transition and you come back down hysteretically. Of course, that means that there's a region in which the two phases can coexist, and that can result in interesting things. So we spent some time imaging this. This is work by my former student, Isaiah Gray. This is, by the way, the focus light version of our microscopy. It's not done with the scanning probe tip, so the spatial resolution is about 0.6 of a micron. This is iron rhodium samples, and when we look at it in the antiferromagnetic phase, so this is way back here at 300 Kelvin, we see this signal from the sample with these individually resolvable domains. And if we do this imaging as a function of magnetic field, what we find is a little bit surprising, which is that we get domain hysteresis within each domain, but in each domain, it's totally shifted to positive M or negative M, and they never cross. This is so-called vertical exchange bias, and it's a relatively rare phenomena in magnetism. And what's actually going on here is there's two subpopulations. So most of the material is antiferromagnetic. Some of the material is unpinned magnetic moments, and due to, for instance, disorder and other things. And what happens is some of those unpinned moments are free to move in the magnetic field, so they switch and you see hysteresis, but some of them are totally pinned by the antiferromagnetic phase, and so they contribute a signal that only points in one direction, and they're the origin of these different domains in the sample. In fact, as we heat the sample closer to this transition temperature, we see a softening of the strongly pinned moments, and we see an increase in the hysteresis, even though we're still below the transition temperature. And then when we go to the transition, we just get this uniform ferromagnetism. One of the cool things about this material then is that you can actually play fun games. For instance, you can use the laser to write in ferromagnetism in the sea of antiferromagnetism. This is in material where the stoichiometry has been tuned to make this hysteresis happen around room temperature. And then you can just erase it by cooling the sample down, sort of neat. Okay, so another thing that I wanted to mention briefly is another look at antiferromagnets using this technique. And here we were interested in current-driven switching in nickel oxide. But the idea was to look at how these domains are actually switching within this material using the spin-Seebeck effect in our microscope. So one of the first things to understand about this effect, the spin-Seebeck effect in an antiferromagnet, is you have to have some way of breaking the symmetry. And so if you, for instance, image a sample that looks like this, where nickel oxide is uncompensated, so that you have a plane of spins pointing in one direction in one plane, and then a plane in the other direction in the other plane, that's nickel oxide 1, 1, 1, then you, in principle, can get a signal from that. If you have an uncompensated interface where every other spin points in opposite direction, then the spin-Seebeck effect from each of these two sublattices will just cancel each other out. And that's just what we see in the experiment. So these are samples grown by MBE in Daryl Shlom's lab. And what you see is the 111 sample gives us nice contrast. In the 001 sample, we get essentially no signal at all. So then we can do these measurements where we're trying to apply currents to the samples and create changes in the Néel order of the antiferromagnet. And what we learned is this is a very complicated situation. You have complex multi-domain states. By the way, these lines you see are actually just polishing marks. They're not magnetic. But you indeed can pass current through the sample and nucleate domains and cause them to grow, for instance. And these things might be understood in terms of spin orbit torques, in which spin transfer torque from the spin Hall effect of platinum is being transferred to the spins in nickel oxide. But you might also understand it from the point of view of just heat and strain, since nickel oxide is a very magnetoelastic material, and you heat it up when you pass a current. So it's actually still not totally resolved. There's some great work from the Clowie group in which they show the effect of strain is very, very strong. Okay, last thing I want to talk to you about for the last few minutes, and I'm going to run out of time, so I will try to skip the more prosaic parts, is to talk about another one of these antiferromagnets using a different technique. This antiferromagnet is a close cousin of the nickel oxide. It's alpha hematite. Except one of the important differences is that through the Dilizinski-Moria interaction, there is a coupling between these two spin lattices that causes a small canted moment. It's a tiny moment because the canting angle is 0.1 degree. So the MS of this material is 2 EMU per cubic centimeter. Sorry for CGS units. And so, but the neat thing about it is that now we have a magnetic handle that we never had in nickel oxide. So I can apply, a few kilogauss to the sample and actually orient it all in one direction, and then I can look at how that affects the domains. Now, people have previously studied this material and come up with different conclusions. This is work from the Ohio State group of Fengyang Yang, in which the expected threefold anisotropy of alpha hematite was apparently observed in current-driven switching. They see 3 different resistance states. Lu Chao Lu's group at MIT looked at this, and they actually concluded that the resistance changes that they see have nothing to do with changes in the Néel vector. They're purely due to like electromigration at the platinum alpha hematite interface. And then there was this work with X-ray imaging in which they see very small changes in magnetization. And it's, basically it's hard to understand what's going on. Okay, so we thought that we might be able to apply another high resolution imaging technique to this, in which we scan a single NV center at the end of a scanning probe. And the basic questions are trying to understand the very complex nature of the domain states in alpha hematite and how that might interact with the switching that we see. So this is work done by my student Nicole Gu, and Nicole is co-advised by Katya Nowak, who's a faculty member in the physics department here at Cornell. Okay, so for those of you that are unaware, the NV center in diamond is a great magnetic sensor because you can read it out optically and it tells you what the magnetic field is. So Okay, I'm just going to jump to, I'm going to go past these imaging modes. I see that Giovanni's turned on his camera. So the point is that we use a variety of imaging modes to measure magnetic fields generated by the sample. Okay, let's just move forward. All right, so here's what we get. In our experiment, what we do is we apply a magnetic field to the sample, but it's only an initialization field. We go to an external setup, we apply a saturating field above a Tesla, it totally saturates the material. Then we take it out of that field and we put it into our imaging setup, which has only a small bias field. First, we apply that field along one of the axes, the crystal that should be an easy axis for the canted moment, and we see this image. And then we apply it in a perpendicular direction, which is along no easy axis, and we see this image. And it seems like, okay, this suggests that this easy axis thing is right. So let's confirm this carefully. So we measured with this procedure along 360 degrees. We initialized it in different directions and then took an anisotropy, or took an image. So, you know, there's kind of two key points here. The first one is that you see these magnetic domain walls and they appear in every image. So pinning is very, very strong in this material. The second thing is that it seems like 0 and 180 degrees are a little bit special and the other ones are not, regardless of easy or hard. And you can see that more carefully this way. So if you just take the standard deviation of the fields that are present in these images, you see only at 0 and 180, you have this increase in the standard deviation. So you have much larger fields produced from much bigger domains. Well, I'll skip this because I'm out of time. Okay, we also did the current driven experiments, and because of the shortness in time, let me just jump to the conclusion, which is we see a lot of switching if we make the initialization magnetic field parallel to the current density and not in the other case. And we quantify this, and again, I think heat and strain are playing an important role here. This still requires quite a lot of work. So I'm out of time, clearly. I think it would be great if we had time for a question or two. So why don't I pause there? You heard the talk. Thank you very much for your attention.